The accepted definition of the term piston engine is an engine in which the working fluid is expanded in a cylinder against a reciprocating piston. This definition could be applied to any reciprocating type of internal combustion engine, but here we'll use it to imply the type of engine used in most light aircraft, namely the four-stroke gasoline spark ignition engine. The piston engine converts the heat energy of the fuel it burns into mechanical energy. This conversion is accomplished by introducing an air-fuel mixture into a cylinder, which is then compressed by a piston. The mixture is then ignited by an electric spark. The subsequent combustion causes a rapid rise in the temperature and pressure of the gases within the cylinder, which forces the piston downwards. This linear piston movement is converted into rotary motion by the crankshaft. When all of the useful pressure has been used, the burnt gases are exhausted to atmosphere. The principle of operation of all four-stroke internal combustion engines is based upon the Otto cycle, originally propounded by Baudrichat in 1876. However, Otto was the first to succeed in producing a working engine using this cycle. The four-stroke cycle involves 4 strokes of the piston and generates 2 revolutions of the crankshaft. The stroke of the piston is the extent of its travel within the cylinder. The lower limit is called bottom dead center, or BDC, and the upper limit is called top dead center, or TDC. The 4 strokes are called induction, compression, power, and exhaust. We'll use a simple single-cylinder engine to illustrate what happens in each of the 4 strokes. The timing diagram for the Otto cycle is shown on the right side of the screen. The induction stroke. At top dead center, the inlet valve opens and the piston descends, creating a depression, drawing the air-fuel mixture into the cylinder. At bottom dead center, the inlet valve closes. The compression stroke. With both valves closed, the piston ascends and the combustible mixture is compressed into the combustion chamber, which is the space formed in the cylinder above the piston when it's at top dead center. The power stroke. A spark plug ignites the mixture and combustion causes a rapid rise in the temperature and pressure. Because both valves remain closed, the increased gas pressure forces the piston down. The exhaust stroke. The exhaust valve now opens as the piston ascends, and the burnt gases, which are now at a very reduced pressure, escape to atmosphere. The piston continues to rise to top dead center, where the cycle begins again. In practice, the Otto cycle proved to be inefficient, and the times of valve openings and closings and the ignition point had to be modified. A practical timing diagram will help to illustrate the reasons for the modifications. Opening the inlet valve before top dead center ensures that it is fully open early in the induction stroke. The time lag, which would normally occur between the piston moving down and the mixture flowing into the cylinder because of the inertia of the mixture, is eliminated. The incoming mixture can thus keep up with the descending piston. The momentum of the incoming mixture increases as the induction stroke proceeds, and towards the end of the stroke is such that the gases will continue to flow into the cylinder even though the piston has passed bottom dead center and is moving slightly upwards. Closure of the inlet valve is therefore delayed until after bottom dead center, when the gas pressure in the cylinder approximately equals the gas pressure in the inlet manifold. As the piston continues to move upwards, the inlet valve closes and the gases are compressed. By squeezing the gas into a smaller space, the pressure it will exert when burnt is proportionally increased. Before the piston reaches top dead center on the compression stroke, the mixture is ignited by a spark. The piston is carried past top dead center by the momentum of the moving parts while the flame is spreading. The intense heat raises the pressure rapidly to a peak value, which is only reached when combustion is complete. By timing the ignition point, complete combustion, and therefore peak pressure, is arranged to coincide with the crankshaft being 10 degrees after top dead center. This allows the engine to gain maximum advantage from the combustion. Most of the energy in the gases has been converted into mechanical energy by the time the piston has moved halfway down the cylinder. If the exhaust valve is opened around this point, any residual gas pressure will start the first phase of exhaust scavenging. Opening the exhaust valve before bottom dead center will also ensure that the pressure of gases remaining in the cylinder does not resist the upward movement of the piston in the exhaust stroke. Finally, the piston moves upwards, forcing the remaining gases out of the cylinder. The exhaust valve is left open after top dead center to permit the gases to scavenge the cylinder as completely as possible by their momentum. The core around which the engine is built is called the engine block. It's usually made from steel alloy. Depending on the manufacturer of the engine, cylinders are bored into or fitted onto the engine block. The cylinders are made of alloy steel. They resist the pressure of combustion and provide a working surface for the piston rings. If the engine is air-cooled, then the cylinders are finned to increase the cooling area. If the engine is liquid-cooled, a large one-piece jacket houses cylinder liners to provide a cooling liquid container around them. Pistons, made from light alloy, are fitted within the cylinders. Around each piston are fitted 2, or in some cases 3, piston rings. The piston rings are made from cast iron, and they ensure that no gases leak from above the piston into the crankcase, where the oil is usually kept. The connecting rod transmits the forces of combustion to the crankshaft, which converts the linear motion of the piston into rotary motion at the crankshaft. The connecting rod is made from H-section high-tensile steel, which combines lightness with the strength necessary to withstand the compressive and tensile loads imposed as the piston changes direction. The connecting rod is joined to the piston by a gudgeon pin, which fits through the small end of the rod, and is joined to the crankshaft by a large circular bearing at its big end. The cylinder head is generally made of aluminium alloy, and is finned to improve heat dissipation. It seals one end of the cylinder to provide a combustion chamber for the mixture. The cylinder head accommodates the valves and the sparking plugs, and supports the valve rocker arms. The valve operating gear consists of a camshaft, or shafts, driven by the crankshaft at half crankshaft speed. The camshaft is driven at half crankshaft speed because each valve is only required to open and close once per working cycle, that is, once every 2 revolutions of the crankshaft. An accessory housing is a casing mounted at the rear of the block. It encloses the drive gear trains for the camshafts, the fuel, oil, pneumatic and vacuum pumps, electric generator, magnetos, and tachometer. During the 4 strokes, the changing pressures within the cylinder can be measured and indicated graphically on a device which produces an indicator diagram. This device is only used during the development stage of an engine. The illustration shows an indicator diagram opened out so that the pressure areas under the curve can more easily be compared and measured. The area within the power column represents work done on the piston during the power stroke. The blue areas represent work done by the piston in compressing the gases and exhausting the cylinder against exhaust back pressure, that is, the pressure which the atmosphere exerts against the outflowing gases. Subtracting the sum of the blue-coloured areas from the area within the power column leaves the red block. The red block is indicative of the average pressure during the working cycle. This is termed the indicated mean effective pressure, or IMEP. We can use the indicated mean effective pressure in a formula which will allow us to determine the indicated horsepower of our particular engine. In the formula, the P represents the indicated mean effective pressure in pounds per square inch. However, we are still required to determine several other values. The L represents the length of the stroke in feet, the length of the stroke being the distance the piston moves between top dead centre and bottom dead centre. The A will be the area of the cylinder in square inches. N is the number of cylinders that the engine has. E is the effective working strokes per minute, or the RPM of the engine. And 33,000 is a constant used to change foot-pounds of work per minute into horsepower. 1 horsepower equals 33,000 foot-pounds per minute, or 550 foot-pounds per second. Bearing in mind that only one function of the formula is variable, that is the RPM of the engine, then it is logical to assume that engine power output is directly proportional to RPM. Increase the engine speed and the power output increases. Decrease the engine speed and the power output falls. The compression ratio of an engine is the ratio of its total volume enclosed in the cylinder with a piston at bottom dead centre to the volume remaining at the end of the compression stroke with the piston at top dead centre. The total volume of the engine is the sum of the swept volume, which is the volume displaced by the piston as it moves from bottom dead centre to top dead centre, and the clearance volume. An example will help to clarify the term. If the swept volume of an engine is 1800 cubic centimetres and its clearance volume is 300 cubic centimetres, what is the compression ratio of the engine? First, we must add the swept and clearance volumes to obtain the total volume. So, 1800 plus 300 is 2100. Then we must divide the total volume by the clearance volume. That is 2,100 divided by 300, and the answer is 7. So the compression ratio of this engine is 7 to 1.